Hello everyone. I'm Pirouz Nourian, PhD researcher and instructor of computational design at TU's Faculty of Architecture. In the next 15 minutes, I'll be presenting a part of my ongoing PhD research supervised by Professor Sevil Sariyevdis. It is a computational model we have made for walkability assessment, which can be used in a computational design process like the one we have reported in a recent paper of us in an urban morphology conference, ESOF, at the. Our definition of walkability is the overall pedestrian accessibility of vital services within a neighborhood. It has two innovative aspects. One is taking account of topographic landscape in calculation of network distances, as well as the topological structure of the network. And the other one is the consideration of an intersubjective aspect of vitality of a neighborhood as the relative importance of places vital services are being provided. For measuring walkability, we have gone through several steps and we have dealt with a number of issues as follows. First, the street network topology, which is how the streets are connected to one another, and that's necessary for measuring the network distance. Second, the topographic features of the neighborhood landscape, and that is necessary for calculation of impedance of the network or how difficult it is to walk certain routes, for instance. And third, the location of vital services as attraction point, and where people generally need to be close by, and the notion of vicinity and aggregation of distance measurements into a single walkability measure. And at the end, the relative importance of points, which attraction points, which results in a polycentric structure of the neighborhood. Okay, first of all, we need to have a solid basis for measuring the distance on the network. We have chosen the shortest path algorithm by Edgar Dijkstra, the Dutch scientist, as such basis. The shortest path is the shortest or the best path that one could take through a network from an origin to a destination. The best path available, of course, and like it is shown in these pictures, as you can see. So it is different if you choose different pairs of origin and destination. And according to this definition, we can have another definition as catchment radius. This actually brings about the other definition, which is the range of distance that could be traversed in all possible directions from a given point. It is called radius because the catchment enclosure will be a circle in case we take the Euclidean distance or the straight line distance between points. Here in this page, you can see two different networks, rectangular and radial, and you can see catchment enclosures with the same radius in case of each network, one for the radial grid and the other for the rectangular grid, drawn from different centers. Notice that a catchment enclosure will only resemble a circle in case the origin is exactly located on the center of a radial grid, not otherwise. In general, the catchment enclosure can be intuitively perceived as the boundary which is delineating how far an agent could go if allowed to go in all possible directions for an equal range of distance. Okay, and finding the shortest path, which is needed for measuring the actual distance between points on a network, we need to attribute a cost or an impedance to every piece of network before running the algorithm. Here is the one which is apparently the most dominant one when it comes to walking a route. Simply its ups and downs. Well, it actually matters in which direction you're going to walk a route. For instance, in this picture, if you are to go through a one-way trip from left to right, for instance, you would only count the upslopes or the positive slopes, while for a two-way commutation like trip, every piece of non-flat network counts and matters. So you need to consider that as the impedance. It has many details. I cannot explain it here in this short time span, but I'll write about it in a forthcoming journal paper. Okay, and to give you a sense of comparison to the actual influence of this impedance, I'll show you two calculations. First, distance between a pair of origin and destination points according to a shortest path, which is when we consider a flat landscape. It takes, for instance, in this case, 22 minutes of walking. And the same trip between the same pair of origin destination points, when we consider a hilly landscape, takes 36 minutes. And you see, this is something we all intuitively know, of course, but it is important to have a method for its automatic calculation. I should let you know that such a measurement is not available even on Google Maps yet. By the way, I forgot to tell you that according to a typical pace of walking for human beings, we can easily interchange spatial and temporal measures of distance with one another. Say, for instance, a 5 km per hour normal speed of walking, approximately, if we take that, one could walk every 80 meters or so in a minute. So this is the way. Okay, here you see a typical imaginary neighborhood. It is chosen as an imaginary neighborhood because we need to be able to do it in any given neighborhood, which is modeled in terms of it's a street network and urban box. And here you can see how network distances are measured from a few attraction points on the network. These attraction points are arbitrarily chosen by the user as the location of vital services. We can show the distance of all locations to an attraction point in a colored gradient map as shown in these three pictures, in which the bluer the color, the farther the distance, respectively. And we can, of course, find the catchment enclosures around the attraction point on the network. Then this question arises, how close are we to an attraction point? As you can see, we need an aggregate measure of distance, as in every point. So far we have found 3 distance values towards 3 attraction points. So we need a way of aggregation. So here you can see 2 distinct ways of aggregation of results. We have named them vicinity and walkability, respectively. Our measure of vicinity indicates how close a point is to any of the existing attraction points, whether point number 0, point number 1, or point number 2. Whereas walkability indicates how close a location is to all attraction points on average, to all of them on average. These two imply quite different meanings. When the points have the same kind of importance, we can use the vicinity measure as it would be all right just being close to any of the attraction points, while in case there are different kinds of services being provided in these locations, and one needs all of them to be reachable by foot, we need to take account of walkability measure. And of course, in aggregation of these measures, it matters how important one attraction point is considered to be as compared to the others. When all points have the same relative importance, we get into a map like the one below, and when the user specifies an unbalanced set of weights or relative importance figures for the points, we get into biased gradients of walkability, respectively. For instance, in this case, point number 0 has the greatest weight of importance. Here, the point number 1 has the most importance, and here, the point number 2. And these weights can be easily changed by the user, of course, and that brings about interactivity in this measurement. And, okay, having calculated all these measures of distance aggregated so far, we get to the point that we need to interpret numbers into not just only colors, but also into verbal concepts such as near or far. It is especially important because these concepts root in our typical human capabilities and preferences. For instance, when a route is 15 kilometers long and flat, we know that it takes almost 3 hours to walk this route, and we consider the destination as to be far, while a route 500 meters long just takes us less than 10 minutes of walking, so the destination is quite near for us. Using a mathematical method named fuzzy logics, we have interpreted distance measures into such verbal concepts and attributed them to the urban blocks where people live, these closed polygons. As it was with the walkability itself, these gradients can be biased when different weights of importance are stated for attraction points, and that actually shows the polycentric structure of the neighborhoods. And we see a distance decay phenomenon, which is geographically very important, sometimes referred to as the first law of geography, that things are all related to one another, but things which are closer are more related. So, and this is modeled as a fuzzy membership function. And you can also see that effect that some authors are referring to as a 700, 800 meters or 10 minutes of walk as the maximum range of a neighborhood. And okay, here you can see the model as a structured flowchart made in a visual programming interface named Grasshopper. We're planning to publish the algorithm soon in a journal paper. And here are a list of references. And yeah, that's it. I thank you very much for your attention. And please provide me with your feedback on this book. Thank you.